Shinsuke Abe will present the topic faint meteor observation by DIMS and the laboratory meteor spectroscopy with many of his collaborators.
Okay, thank you for introduction, Yulei. So can you see my screen on full size?
Yes.
Yes.
Okay. Okay, so I can start my presentation. And thank you very much for organizing IMC on internet. So unfortunately, we cannot drink each other, but I hope we can enjoy this meeting online. So today's my topic is about a faint meteor observation by DIMS. I will explain DIMS later, and laboratory meteor spectroscopy. So first of all, I would like to apologize because we planned to obtain the data from DIMS last month, but in Japan, we had a very badly weather last month due to typhoon and so on. So far we have no data. So I changed my title slightly, and I included the laboratory experiments of meteor spectroscopy in this presentation. So here is my colleagues, and this is the international collaborators. And Professor Kajino is a principal investigator of this project. Okay. So DIMS. DIMS is the Director and Interstellar Meteoroid Study. This experiment is aimed at searching for microscopic dark matter, such as so-called nuclear lights and strange quark matter, which can be observed at the altitude around 30 kilometers by their interaction with the Earth's atmosphere. And it can be seen like a very fast meteorite with the velocity around 250 kilometers per second. So since this dark matter candidate can pass through the Earth, this meteor, the direction is not only from the sky, but also from the ground. So from everywhere we can see this phenomenon by the theoretical prediction. And also our camera system is sensitive enough to detect interstellar meteoroids. So that's why DIMS project is aiming both meteoroids, interstellar meteoroids, and nuclear lights, like a candidate of dark matter. So the DIMS experiment system is under construction, and which will be installed at the Cosmic Ray Experiment Facility in Utah State in USA, hopefully next year. So original plan, we can start this observation from this year, but due to the COVID-19, so the schedule is slightly delayed. And the detail of this system and the very fast result will be presented by Dario later in this conference. So please look at his presentation later. So anyway, we can distinguish both phenomena by their trajectory and their altitude. So that's our purpose to observe these two phenomena. So this is a DIMS system. The background is just an example of the meteor image detected by DIMS camera. So DIMS experiments system consists of 4 high sensitivity camera modules, each of which will be installed at site about 20 kilometers apart. So far we are using probably currently most sensitive black and white camera in the world, developed by Canon. And this is back illuminated CMOS camera. and maximum ISO is 40,000. Oh, no, 400,000. It's crazy, but in the city, because of city light, we didn't test with this high performance because we need a very dark sky, and we can record high definition image quality with 30 frames per second or 60 frames per second. So now we are testing. This is the final shape of this system. We can block the sunlight with using this roof. And the video image are taken by the high sensitivity cameras at the frame rate 3160. I explained, and so far we are using UFO capture as a trigger to record the meteors. But in the future, we plan to develop our own software to detect much fainter phenomena in real time. This is the future plan. And also, this camera has a solar power supply system because some of the station has no power supply in the desert. And the Arduino interface to control the fans and heater by monitoring sensors. So, okay, this is a picture of the inside system controlled by Arduino. So we can control this system remotely. Even the power was cut, we can turn on the power and change the direction of the camera and correct the data and send the data automatically. So this is an example of measured temperature and relative humidity for 2 days in Japan. Yeah, we just start test observation in Japan from this spring. So this is these are cameras installed at my university. Nihon University is located near Tokyo area, and Osaka Electric Communication University in Osaka City, and Professor Kajino is located at Kobe, and we started test observation in the very strong city light from the spring. So even in the strong city light, we can detect many meteors during Lyle's meteor maximum. So we tested DIMS camera for about 3 months. Then we moved our camera system to another location in Yamanashi and Nagano prefectures. So last month, I and my student and Professor Kajino installed this camera at the Akeno Observatory. This observatory is operated by Cosmic Ray Institute of University of Tokyo, located at Yamanashi Prefecture. So this place has it's not perfect place, but it's very convenient, about 2 hours from Tokyo by driving. And yeah, we installed this camera last month, and then we plan to do the same triangulation observation using the second camera at the Kiso Observatory. However, the typhoon hit during our observation, so we had no data. And last month, statistics is not so good because of bad weather in August and September. So anyway, it's using 85 millimeters focal ratio 1.4 lens. We can detect a lot of meteors there. So I didn't analyze in detail, but I just showed the very tentative result pictures. So this is Akeno Observatory, controlled by Institute for Cosmic Ray Research, University of Tokyo. And another observatory is Kiso Observatory, Institute of Astronomy, University of Tokyo. So this place is the best place for observing meteors. So far, you can check the YouTube, and the Asahi newspaper installed their color camera, Sony color camera, and we can check their video image from KISS Observatory and also from the top of Hawaii Island, so on YouTube. So you can check the Asahi web camera, Meteor web camera. So we plan to install the second DIMS at the KISS Observatory. So now they are doing construction for power supply and LAN cable for only for our instruments. So we plan to install, fully install, hopefully end of next month. And we will start triangulation observation from this autumn or early winter. So this is my first talk, and I will slightly change my topic about spectroscopy. As you see, this is the test chamber, and you can see the meteor wave just before the hit the sun in the chamber. Basically, this test was done for checking the impact flash to simulate the lunar impact flash. And then I realized that we can generate a meteor in the chamber with high pressure condition. So recently, we succeeded to take a very high speed meteor wake spectroscopy using this facility. And because so firstly, we use the polycarbonate. This is just a plastic ball with the diameter of about 5 millimeters. And so we are interested in the, for example, the delivery of organic matter to the early Earth or present Earth. However, the lack of observed molecular carbon and molecular CN emissions in the operating meteoroids are reported. So firstly, I want to check the emission from carbon itself. So this test was succeeded. So with the atmospheric pressure using about 600 Pascal, it's compared to the altitude of about probably 30 to 40 kilometers in the Earth's atmosphere. So because low velocity, about 6 kilometers per second, we use lots of atmosphere. That's why the pressure level is very high. So this spectroscopy is taken by the exposure time 1.7 microsecond with 500,000 frames per second. This is the very, very fast spectroscopy. So this, the left-hand side is a zeroth image, and right-hand side is the first stage. And compared with the molecular model, assuming the thermal equilibrium condition, and also assuming the electric vibration and the rotational temperature are the same, we can estimate the LTE temperature around 5,500 Kelvin. And during this event, about this image, the temperature is almost constant, around 5,500 Kelvin. And we also check the black body temperature using the slope between 600 and 750 nanometer region. The black body temperature, mainly from the head of the meteor, is about 3,000 Kelvin. So anyway, we confirmed molecular carbon emissions, so-called swan bands, in the visible wavelengths, because this artificial meteoroid is consisted of lots of carbon, so we can easily see the carbon emission. So this is another interesting result. We see the fragmentation of this artificial meteors. So you see these very faint fragmentations. And we check the dynamics of this fragmentation. And interestingly, the deceleration velocity is about 8% of the meteor itself. This 8% is almost the same rate of Leone's jet structure reported by Mike Taylor in 1999 from Leonid March airborne campaign. So anyway, this was just happened. So we cannot control fragmentation in this chamber. So probably the metal, this polycarbonate was already damaged and it can easily broken in the chamber. So recently we started another test using the two-stage light gun. This is the vertical, this is a horizontal gun, and with velocity about 7 kilometers per second. So you can see the video.
はい、実験2日目です。
What's done
優勢が光ってくれないの
by
で
my laboratory
3000パスカルでやることになりました。
just 1 month, 3 weeks
今
ago.
カメラ準備中です。
My students used many cameras to record this phenomenon. So the length of this hyperburst input facility about 10 meters. So here is an ejection part. So we can check the time of velocity using the time of flight here. And then, so inside the chamber is normally vacuum, but we control the vacuum level, pressure
こ
level.
こでトリガーかけてます。
Using time of flight, we use this timing as a trigger to start the high-speed camera to record the imaging and spectroscopy. This camera is for imaging, high-speed camera, black and white.
はい、これファントムの白黒の方ですね。レンタルしてるカメラです。GoPro とアテック。こっちにキー
And
プ
we
ロですね。
also
キー
do
プロとマ
the
ヤ。
fiber spectroscopy. It's not fast spectroscopy, but exposure is only 8 milliseconds. So we can take only one shot. But using the quartz window, CAF2 window, we can detect both ultraviolet and near-infrared spectroscopy using
分
two
光器
spectrograms
これは
from 250 nanometer
に変えてあ
up
ります。
to 1200
もう一つファントム
nanometer.
これカラーのファントム
These are
を
color
つけてます。
high-speed camera
はい。
with
この映像はですね、
longer
こ
focal
れミラ
length
ーで
and
折り返して、
the
倒立像を撮るように
reflection light is reflected by the mirror. We can take the image.
垂直方向からですね。
And the main spectroscopy was done by this high-speed camera using the transmission grating at the objective place, like observing meteor. So that's why so there is a distance between the window and the camera. So you can observe this
カメ
meteor
ラを
phenomena like
横に
of
してですね、画角の長い方が分散方向になるようにあえてカメラをこのように傾けてます。300本パーミリの低分散分光器をつけています。はい、こんな感じですね。
we have about 13 cameras operated by 5 people. Okay, this is just an example of high-speed imaging of meteor ablation. So at this time, we used a kind of iron particle with a diameter of 1 millimeter, with a velocity of 7 kilometers per second. And the atmosphere level is very, very high, 3,000 Pascal, because this is just test to generate the meteor itself. So anyway, we can see the meteor head and the ablation wake. So after checking the crater generated by this impact, there is only single, very beautiful single crater. It means that these fragments are almost zero mass. It's only the surface can be ablated and to generate this meteor wake. And here is a color image with zoom up lens, and the exposure time is the same, so we can see some particles here. This is very preliminary high-speed spectroscopy. So now we succeeded to record these phenomena, and the next experiments will be next month. So we will take the very high quality data next month. Okay, so this is my final slide. So DIMS 2, dark matter and faint meteor spectroscopic observation will be planned, and I'm now applying the budget. So if this budget will be succeeded, I hope to establish the new camera at the Haleakara Observatory and Mauna Kea Observatory. So recently, Tohoku University in Japan established their own telescope observatory, 1.8 meter telescope at Haleakara, and they asked me to put my meteor camera there. So that's why I have some negotiation with them, and also Subaru plays, and I hope to collaborate with Amos camera with Slovakian people. Okay, thank you very much.
Thank you very much, Shinsuke. So you have a privilege to have slightly more time than other speakers because you were the first one, and as we know, the first one has the more tough.
On time.
Yeah, but we have still some few minutes for the discussion. So, but if you wish, you can applause virtually to Shinsuke, and then I already see raise hands of Sirko Molan. Sirko.
Hey, Shinsuke, I'm not fully sure if I got your first slide right. When you say about the DIMS experiment with the interstellar meteors, that they're moving from all directions, so even upside down. Can you quickly explain on that, how this may happen?
I'm not the specialist of dark matter, but there is a hypothesis of the so-called nuclear lights. It's depending on their the mass, and the larger mass can pass. I'm not sure, but some of mass particle of dark matter candidate can pass through the Earth itself.
Okay.
I cannot explain it. Sorry. Probably Dario will explain in later.
Thank you.
Sorry.
Okay, and Peter Slansky? We couldn't hear you, Peter. Still, you are muted somehow.
Hear me now?
Yes, now it's better. Yes.
Okay, so it's a problem with the headphones. Yeah, thank you very much for your presentation. I envy you for those cameras. I've worked with the ME20 once. I have two questions. What software do you use to detect the meteors? And second, what was the dimmest meteor you have detected with the Canon, with the DIMS?
Yeah, good question. So far, we use just commercial UFO capture, the Sonotako UFO capture. But the problem is that the detection level is not so good. So in the future, we will prepare on software to detect faint meteors. So far, we are using UFO capture. And the faintest meteor is depending on the focal length of the lens. And with large field of view using 35 millimeters, the limited magnitude is only 6, 7. So recently we changed the lens to 85 millimeter.
Yeah.
And I think it's just rough estimation. It's about 8/9 magnitude.
Okay. How do you calculate this this measurement of the magnitude of the meteor? Does it by UFO capture?
So far, UFO analyzer, but I check the field stats by myself using IRAF.
Okay.
But anyway, we will summarize the first result in the near future.
Thank you very much.
Okay.